And so my research focuses on microplastics in Muskoka-Haliburton headwater lake catchments. So plastic is a common term used to describe the synthetic and semi-synthetic material used to manufacture industrial products. Plastic was first developed in 1856 by Alexander Parkes, who invented Parkinson, but the mass production of synthetic plastic did not begin until 1907, when Leo Baekeland created Bakelite. The picture on the top is a fishing spool with yellow Parkinson side guards, and the picture on the bottom is jewelry made from Bakelite plastic. Since then, the production of plastic has rapidly increased to the point that 368 million tons of plastic was produced globally in 2019. This is greater than the entire weight of the human population. Of the plastic that is produced, 91% is not recycled. Discarding plastic waste is problematic as plastic is highly durable, resistant to degradation, and plastic is mismanaged so it can escape our waste system either accidentally or intentionally, such as through littering. It can take hundreds or thousands of years for plastic to break down, and only a small quantity of plastic can be recycled. Therefore, the majority of plastic produced is either disposed of via the landfill or ends up in the natural environment. In the natural environment, inland plastic that has either been accidentally lost, carelessly handled, or intentionally dumped can be carried to larger water bodies via rivers and streams and will ultimately end up in the ocean. Buoyant plastic can be transported and dispersed, captured by shorelines, or lose their buoyancy and sink deeper into the water column or settle into the sediment. Plastic can also be degraded into smaller pieces, giving rise to microplastics. Plastic and microplastic pollution is not strictly limited to the ocean. Rather, microplastics have been detected across the globe. Microplastics have been found in water and sediment in the deep sea, Arctic and Antarctic, in remote mountain catchments such as Mount Everest, in organisms such as shellfish, and even in the air and rain over cities, mountains, and national parks. Microplastics have also been found in drinking water, bottled water, beer, salt, honey, and in some tea bags. So this brings us to the question, what are microplastics? Microplastics are plastic particles less than 5 millimeters in diameter that can originate from primary and secondary sources. Primary microplastics are manufactured to be microscopic in size, such as microbeads that are used in personal care products like toothpaste and facial cleansers, cleaning products, and textiles. Secondary microplastics are fragments that arise through the breakdown and weathering of larger plastic pieces currently in the environment. An example would be a tiny plastic piece that arises through the breakdown of a plastic water bottle. Microfibers are a subset of microplastics and are either released directly into the environment during textile production or arise through the fragmentation or wear and tear of larger synthetic textiles, such as clothing. The 4 pictures on the left are examples of different types of microplastics. The atmosphere is one of the main pathways of microplastics to the environment and is the primary source of microplastics to remote and isolated regions. Microplastics can enter the atmosphere through wear and tear of clothing, during laundry drying, from the abrasion of car tires, as well as from the resuspension of dust and particles already on the ground. Wastewater treatment plants are another major source of microplastics to the environment, as microplastics found in personal care products or microfibers found in washing machine discharge after clothing made from synthetic fibers, such as polyester or nylon, have been washed, are not fully removed during the treatment process, and are therefore released into the natural environment, along with the wastewater effluent. Other pathways may include stormwater and surface water runoff, and anthropogenic activity, such as fishing, sporting, and shipping. In the figure here, the microplastics are represented by red circles, and we can see that wash off from roads and the streets, which can be seen right here, go into storm drains, which then enter into rivers and will ultimately make their way into the lake and the ocean. Microplastics may pose a serious risk to organisms as they remain in the environment for long periods of time, have a tendency to be ingested, and may cause physical harm to organisms via blockage and abrasion when ingested, and have the potential to accumulate throughout the food web. Microplastics can absorb and accumulate toxic compounds, such as pharmaceuticals, trace and heavy metals, and pathogens, and the ingestion of microplastics and their associated chemical additives can have negative impacts on organisms when ingested. There is also concern for potential exposure to microplastics or microfibers via inhalation. There are a number of different studies which have shown that microplastics have an impact on organisms, but there are also a number of studies which show that microplastics do not affect organisms, so more research is still needed in order to determine the full impact of microplastics. The majority of studies on microplastics have focused on the marine environment. The few studies that have been conducted on freshwater environments have focused downstream of wastewater treatment plants or urban environments. Very few studies have been conducted on headwater lake catchments. Headwater lakes are lakes that only have rivers and streams flow into them, with no lakes upstream from them. They are the furthest most upstream body of water. Despite the atmosphere being identified as one of the main sources of microplastics to remote regions, only a handful of studies have examined microplastics in the atmosphere. Of those studies, only 5 have been conducted in rural or remote regions. Furthermore, no studies have been conducted to determine the microplastic budget for headwater lake catchments, so similar to your financial budget, measuring how much comes into the lake, how much leaves the lake, and how much stays in the lake. Therefore, the objectives of this project were to 1, estimate the abundance of microplastics that fall from the atmosphere to 4 background monitoring stations in Muskoka-Haliburton, and 2, estimate the quantity of microplastics coming into and out of 3 remote headwater lake catchments in Muskoka-Haliburton, specifically looking at inputs from the atmosphere and inflow streams against outputs from outflow streams and sedimentation to lakes. The Muskoka-Haliburton region has been part of a long-term monitoring network which assesses the impact of cottage development and long-range atmospheric transport of pollutants on water quality. The 4-decade-long monitoring program is operated by the Ministry of the Environment, Conservation and Parks at the Dorset Environmental Science Centre. The region has been heavily studied, so there's a lot of background information on the lake catchments, and well-established sampling sites have already been set up, which are regularly sampled for chemical analysis. Through a partnership with Trent University and the ministry, I was able to build off of the ministry's sampling regime and have extra samples be collected for microplastic analysis when the ministry did their routine sampling. The first study conducted focused on 6 monitoring stations, PT1P and PT3P, which are located near Paint Lake and are on here the map, SE2P, which is located near Solitaire Lake, HYP2, which is located near Heaney Lake, and PCP and PCP2, which are located near Plastic Lake. Some of the stations do receive some influence from anthropogenic activity. So PT1P and PT3P, which are located in yellow and purple on the map, are located adjacent to the Dorset Environmental Science Centre and may be influenced by the presence of people at the facility, parking lots, and roads. SE2P, which is located in blue on the map, is located close to the Limberlost Forest and Wildlife Reserve, which is a private forest that contains more than 70 kilometers of trails accessible to the public. These stations, however, are still remote stations. The second study focused on 3 headwater lakes, Plastic Lake, Harp Lake, and Dickey Lake, and their associated inflow and outflow streams, in addition to the precipitation stations located near the lakes. There is some cottage development on Harp and Dickey Lake, with cottages being predominantly serviced by septic systems. Precipitation or rainwater samples were collected as microplastics in the air can settle to the ground like dust or can be deposited by rainwater. Inflow and outflow streams were collected as microplastics in the inflow streams can be brought into the lake, and microplastics in the outflow streams microplastics in the lake can be left through the outflow streams. Lake water and sediment samples were collected as microplastics that are in the lake can lose buoyancy and sink to the bottom of the lake where they become trapped in the sediment. Precipitation or rainwater samples were collected for 13 months at either weekly or bi-weekly intervals using a bulk precipitation collector, which can be seen here. Samples were also collected using a wet-only collector, which is similar to the collector seen here. However, it has a cover which automatically opens when it rains, so it is not continuously exposed to the air like the collector seen here. When there was sufficient volume in the collectors, the bags were removed, transported back to the lab, and poured into bottles. This is the standard way that the ministry collects their precipitation samples. Stream samples were collected bi-weekly or monthly as grab samples from the 17 monitored inflow and outflow streams between May 2019 and March 2020. Lake samples were collected monthly from the deepest point of the lake, 1 meter below the surface, between May 2019 and November 2020, and once again in late August 2020, where samples were also collected from the top, middle, and bottom layers of the lake. Duplicate sediment cores were collected from the deepest point of the lake using a gravity core, which can be seen on the picture to the left. The sediment cores were extruded onshore for the top 0 to 3 centimeter section. So the gravity core sinks to the bottom of the lake and sinks into the sediment, allowing for a long tube of mud to be collected from the bottom of the lake. This can be seen in the picture to the right. Sediment cores can then be used to interpret past events or what the lake system was like at different periods of time, as each year new sediment particles stack on top of each other, similar to how dust settles and accumulates in your home. The sediment cores can then be dated and used as a timeline for different events. In this case, we were only interested in the 0 to 3 centimeter section, as this corresponds to the past few decades. The sediment samples were oven dried at 55 degrees Celsius for 72 hours to remove all the water that was present in the sediment. 55 degrees Celsius was used so that any plastic present in the sediment does not melt. 3 grams of sediment was then digested in a hydrogen peroxide mixture for 1 hour at 55 degrees Celsius to remove any organic matter present in the sediment, such as leaves, which can make it difficult to see and identify the microplastics. The digestion process is similar to how our stomachs digest and break down food. The samples were then sieved and density separated for 10 minutes in zinc chloride. Zinc chloride has a density heavier than water and plastic, so any plastic that is present in the sediment sample will float to the top, while any remaining organic matter that did not break down, such as rocks, will sink to the bottom. This makes it easier to remove the microplastics from the sediment. The samples were then vacuum filtered through separate filter papers and analyzed under the microscope. The lake, stream, and rainwater samples were vacuum filtered through filter papers, which can be seen in the picture to the left, stored in petri dishes, and visually analyzed under the microscope. If 2 or more of the visual identification criteria are met, which can be seen in the top right, the particle was classified as an anthropogenic particle, i.e. synthetic but not necessarily plastic, and the number of criteria met was recorded. Each anthropogenic particle was then photographed and measured, which can be seen in the bottom right. An example of an anthropogenic fiber would be a cotton fiber from jeans, which is a natural fiber that has been stained with a number of different anthropogenic dyes. Of the anthropogenic particles that were identified, 20% were randomly selected and tested using the hot needle test to determine the proportion that were plastic. An example would be a polyester or nylon fiber. If the particle melted after being touched by the hot needle, it was classified as plastic and was further examined using Raman spectroscopy to determine the type of plastic. Raman spectroscopy is a machine which can be seen in the picture at the top, which shoots a laser onto the sample and produces a signal or a spectrum, which can be seen in the picture on the bottom. The signal or spectrum can then be compared to a library to identify the plastic. In the picture on the bottom, the black line is the spectrum for the identified microplastic, and the red line is the spectrum for the plastic polypropylene. The two lines are very similar to each other, so we can identify the microplastic as being polypropylene. Microplastics are everywhere, so open Petri dishes with filter papers inside of them were left out while I completed my lab work to capture any microplastics that could have potentially fallen from the air onto my samples. Be Pure water is ultra pure water that was used to rinse and clean any lab equipment. The water may contain fibers or microplastics, so it was filtered before being used. All equipment was triple rinsed prior to use and covered in aluminum foil when not in use, in order to prevent contamination from microplastics that may be present in the air. Lastly, clothing contains plastic such as polyester or nylon, so to prevent any contamination from clothing I was wearing, a cotton laboratory coat was worn for all laboratory processes. The daily rate of microplastics falling from the atmosphere ranged from 32 particles per meter squared per day at Plastic Lake to 73 particles per meter squared per day at Paint Lake, with the average rates across all study sites being 57 particles per meter squared per day. This can be seen in the figure on the right in the blue bars, which should be right about here. So this is equivalent to approximately 400,000 particles falling on a soccer field every day. So the highest rate of anthropogenic particles falling from the atmosphere observed at Paint Lake is likely due to the fact that the site is influenced by anthropogenic activity, specifically from the presence of people at the Dorset Environmental Science Center. Synthetic particles easily tear from clothing during wear and can become suspended in the atmosphere. Of the anthropogenic particles that were tested using the hot needle test, 12% melted and were identified as plastic, therefore giving us a plastic deposition rate of 7 microplastics per meter squared per day. That can be seen in the orange bars on the figure. So this is equivalent to approximately 50,000 microplastics or 22 meters of plastic falling on a soccer field every day, or 18 million microplastics equivalent to approximately 8,000 meters of plastic falling on a soccer field every year. One thing to note though is that the width of microplastics are very small, often less than 0.5 millimeter. So while the length may be long, such as 22 meters, the width is very, very narrow. After quantifying the number of plastics that fell from the atmosphere, we wanted to know how important the atmosphere is as a source of microplastics to lake systems compared to the inflow streams, and how it compares to the outflow stream and sediment. The daily rate of microplastics coming into the lake was highest for the atmosphere, approximately 3 times greater than the inflow streams. This suggests that microplastics falling from the atmosphere can account for all of the inflowing microplastics to the study lakes, and that a large fraction of the microplastics that fell from the atmosphere are retained in the terrestrial catchment or the land area surrounding the lake. The rate of microplastics leaving the lake was greater in the outflow streams for Plastic Lake, but for Harp and Dickey Lake, the rate of microplastics settling to the lake sediment was greater. This can be seen in the figure on the left here, where the blue bars represent the rate of microplastics coming into the lake, the orange bars for the inflow streams, the gray bars represent the rate of microplastics leaving the lake, and the yellow bars are for the sediment. In order to understand how microplastics move in the environment, we wanted to create a microplastic budget for the lake. So again, similar to your financial budget, we look at how much comes into the lake, how much leaves the lake, and how much stays in the lake. So the daily microplastic input rate to the study lakes range from 3 to 16 million microplastics per day, with the daily microplastic output rate ranging from 2 to 10 million microplastics per day. This can be seen in the blue and orange bars in the figure. This means that there is a high retention of microplastics in each of the study lakes, with between 2 and 7 million microplastics being retained in the study lakes on a daily basis. If you were to line all of the microplastics in a row, it would equate to between 800 and 3,000 meters of plastic. Again, one thing to note is that the width of microplastics are very small, often less than 0.5 millimeter. So again, while the length may be small, the width is still very narrow. So this suggests that lakes are a large storage unit for microplastics, holding up to between 30 and 45% of the microplastics that come into the lake. The microplastic residence time, or the average time that microplastics spend in a lake, range from 3 to 8 years, meaning that it takes between 3 and 8 years for the microplastics that are found in the lake to leave the lake. Polyamide, also known as nylon, and polyethylene terephthalate, also known as polyester, were the two most common plastic types identified in this study. Of the microplastics that fell from the atmosphere, nylon and polyester comprised 24% each, and in samples collected from the lake catchments, 16% were nylon and 28% were polyester. These plastic types are commonly used in textile industry, with nylon also being used in the production of car tires, as well as in fishing gear. Other plastics that were identified but were less common included polystyrene, polypropylene, and polyethylene. Blue and red were the most common colored particles identified, with less common colors being green, pink, orange, purple, and yellow. Fibers were the dominant shape identified in the atmosphere, lake water, and streams. However, in the lake sediment, there was an equal proportion of fibers and fragments. The prominent nature of fibers in the atmosphere is likely because fibers easily detach from clothing during laundry drying and everyday wear, and because fibers can remain suspended in the atmosphere longer, allowing them to travel to remote regions or globally. Fragments, on the other hand, may deposit closer to the source. The pictures on the bottom here is a red fiber, and then you can see a blue fragment on the right. So what can you do to reduce plastic and microplastic pollution? So each year, 22 billion plastic bottles are thrown away, which is enough plastic bottles to circle the earth 4 times. And approximately 90% of the plastic that is disposed of is single-use plastic. Improving recycling waste and reducing the use of plastic would put a major dent in the quantity of plastic entering the natural environment, and consequently would reduce microplastic pollution as larger plastic waste does break down to smaller microplastics. To reduce single-use plastics, you could use a reusable water bottle rather than buying plastic bottles. Bring your own bag to the grocery store and use a travel mug or your own straw to reduce straw and coffee cup waste. Lastly, cleaning up litter and avoiding products that contain microplastics are other ways to help reduce plastic pollution. Thank you very much.